Hello, good morning everybody. I would like to welcome you to this second lecture on semantic segmentation on the computer vision course. I would suggest we do the lecture first, and then in the second half we will discuss the homework from last week and the new exercises for this week. So last week we started with this topic of semantic segmentation, and we looked at some actually just segmentation techniques that were a bit borrowed from unsupervised learning. So last week we had the problem that we actually just had an image of probably some color values like RGB, and we tried to find out some regions in that image by using some features or so that the regions are similar with. Like, for example, we could go to the color space, we could cluster in color space by k-means, and then all the pixels that come up in the same cluster would be one of those regions. So now today we really want to go in the direction of semantic segmentation. That is, we don't have just the images a starting value, but we also have labels of the classes that we want to detect in the image. And as you remember, for the semantic segmentation, we want to assign some classes on some pixel level. So input is again image with RGB values, so this will be a two-dimensional arrays with 3 channels, for example, and additionally kind of image of the same size where we have integer labels of the classes that we want to find out here. So of course, for then supervised learning, we want to try to teach some algorithm that when the algorithm gets a new image, it will be able to produce the labels, the class labels for that image on a pixel level. So how can we do that? Now, if you only have the raw input pixel value, and from one pixel value, we would like to find out what class that pixel is. That will be a little bit difficult, except if the problem is very simple and maybe you could just deduce the class from the color alone. So more often you will not want to use the pixel only, but you would like to use at least some neighborhood of the pixel in order to better classify what the class of that pixel in the center here is. And so one idea would be just to use the raw pixel values of that regions, but this will be a lot of values, and for most supervised learning algorithms it's not feasible just to work with those raw pixel values. We will see that when we use deep learning, then we can use the raw input values, because the deep learning will first learn some pre-processing step to actually gather the information from this area. If we don't have this feature in the training algorithm, then we must come up with the features ourselves. So usually what we have is we look at some neighborhood of the pixel, and we have some feature calculations that will calculate some features of the neighborhood, and then we will have a feature vector for each pixel, and from this feature vector we would like then to derive the class. So here's some examples, like high-level example of what a feature is or what a feature should be. So the feature should calculate some properties of an image or from image region and kind of uniquely describe that image. So if we use features, for example, just for a recognition of images, like to find out from a whole image what class that is, then common feature, a descriptor we will see later that is depicted here is like the sift feature. It finds some specific points in the image, so-called key points, and then try to derive some features in the neighborhood of that points which uniquely describe this part of the image. And so the idea is that then if you have another image which looks similar here, it will have the same feature vectors, and then you can compare like the image with the feature vectors, and same feature vectors will then probably be the same class of the image. These features can also be used in other image processing tasks like find subregions. So if you want to find that subregion in a larger image, or maybe for image stitching by the features and so on. Whatever you do, however you calculate the features, even at different points or at all the points, at the end you will concatenate them all together and you will get one feature vector there. Well, so if you want to have some feature calculation, then we must derive some good features. Like what, for example, would we like to have from those features? So what properties should good features possess? Any ideas? RGB, somebody said. That means yes, you should be able to calculate it from all the color values. Robustness, yes, good point. Question a bit, how would you define robustness in that thing? So I think you could mean robustness that if you have a small change in the image, you don't want to feature to change too much. And I think that would be a very good property. So maybe you can also think of what those small changes in the image would be that we want to be robust against. Yeah. So somebody said easily separable. So you want to have them, I would interpret it as you want to have them really typical for that feature, for that classes that you want to detect. So it depends a bit on the tasks at hand. Yeah. Okay, some normalization. Normalization is always good. You need then in the supervised learning algorithms. One input, you don't want them to depend on the position. Yes, that is very good. So if you want to detect some texture, we will see, or also later some class, it doesn't matter where it is in the image. So you want to have it invariant to the position, and I think these invariants, or also as was mentioned, robustness is some key aspect of the feature that you want to have. So you would want the features to be invariant. Now there's some possibilities here where they're invariant from, but there are also more of that. So as you have mentioned, independent of the position means invariant to translation. So does not depend where the feature is calculated in the image. It will be the same feature if the underlying textures is the same. Usually when you use a neighborhood of an image or use filters to calculate the features, you will get that property more or less automatically. A property that you will not necessarily get is rotation invariant. So maybe we will use that like a semantic segmentation for like texture segmentation, or we will see for maybe some medical issues to detect Handectzema. So then the images that you get at the beginning, they might not always be in the same rotation. So if you have an image and a slightly rotated image, you would still like to be able to detect the same classes. So your features need to be rotation invariant. And they might not always be on the same scale, so they also need scale invariant. And the last thing I think is also some robustness, like if you have some small changes in the feature, or if your photo is a little bit different with a little bit different illumination, you should still be able to get the same or similar features. There was a question, skewing is also a form of translation. It would be a form of transformation, not translation. So good point. It could be skewing is something that could be present when you have some perspective changes. So there would be even a further class of transformation. So for example, if you have some perspective transformations between the images, you could make the features invariant to that too. Sometimes you only look at some local transformations, so the more global transformations like that might not be such a big issue then on the overall image here. Okay, so these are some invariances that you want to have the features to have. And now let's look at some features. So in the next few slides, we will go through some more commonly used features in image processing, and especially our task will be a little bit texture segmentation, so that if you have some pattern in the image, we would like to describe to find that pattern. That's also what we then want to do in the exercise. So we will look at first at some features that have been developed exactly for that. So one feature here that is called local binary patterns. It is quite a bit low level, and the idea is that it assigns some code to the neighborhood of an image, and those code is then used as a feature vector, as a feature value, as a descriptor. The code is made like that you have you look at one image in the one pixel in the center of a region. So let's first assume that it's just a 3x3 region. It can later also be a larger region, and it could be just the pixel values, or it could be the pixel values smoothed by some Gaussian filter if you use a larger radius. So you have your center pixel, and then you compare each one of the pixels with the center pixel, and wherever the pixel is greater than the center pixel, you mark it as a 1. And if it's not greater, then you mark it as a 0. So you get 1, 0, 1, 0, 0, 0, 1, 1. So you see it's quite binary. And then that's a bit also the low level thing of it. You just combine it to some integer as a binary descriptor and use that as a feature value. Of course, you could also use it like as this binary vector or some hot encoded format. That would also be possible for some of the algorithms. The idea behind this is that you can detect if, for example, the region is rather smooth, or maybe the region has a sharp edge on this point here, so that all the pixels on one side are lower than the pixels on the other side, and this will kind of describe you the picture neighborhood at this position. So how about the invariants? I think we have some translation invariants. We also have some invariants by illumination, because if you just increase the value of all the pixels, then the local pattern here will not change. But you're not rotation invariant and you're not a scale invariant, but they have come up with some additional method of calculating these binary patterns to make them rotation invariant, and also kind of scale and more gray level invariant. So one is first that you use different radius that you calculate your points, and then you have more features that you can use for that. And the second, to the rotation invariants, you can actually classify all the possible outcomes of which pixel could then be higher or lower than the center pixel, and make them kind of rotation invariant if the positions where it's higher and lower do not actually depend. So for example, you would then come up with just 36 rotational invariant features. So the idea here is, for example, you have this one. Okay, here let's say the pixels are all lower than the center pixel. There is only one possible configuration here. And then you have this configuration here where you say, okay, 1 pixel is higher and 7 are lower. And now this will be the features, and it will be rotation invariant, because it does not matter where this higher occurs. So if the higher occurs here, it will also be mapped to this class 1 of the features. So you have just one set where you only have one higher one. Then you have one class where you have two that are higher that are next to each other, three that are next to each other, and so on. And you can calculate all the possibilities where the higher values could be, rotation invariant, and you get these 36 different features here. So luckily you don't have to calculate things like that yourself, but libraries have implemented then this algorithm, so you can just say you want it rotational invariant, and then you get that version then. Okay, so that was one feature example. Another feature example, which occurs very often, is filter banks, so that you use different filters and you use the filters in different directions. So common filters you might know from some earlier image processing tasks are derivatives of the Gaussian. For example, the first derivative of the Gaussian, which is depicted here, is a good edge detector, and so you kind of use features as edge detector, so you will know, okay, if there's an edge here, then you will get a high response to these features, and you use them here in different directions and in different scaling. You can also use the second derivative of a Gaussian, which is actually a good line detector. So if you have small lines in the image, then those will be detected. And then you have just the Gaussians themselves. So this is a common filter bank for edge and line filters at 6 different orientation and scales, and the Gaussian, and the other is actually a Laplacian of the Gaussian. To make that rotation invariant, you can use the so-called MR8 filters. We will just then use the maximal response of all this. So if you have this scaling level, and instead of using those 6 values, you will only use the maximal values of those 6 responses, and then you get a rotational invariant features with 8 values, namely 1 here, 1 here, 1 here, then another 3 here, and those 2, they're already rotational invariant, gives you 8 features. Here's an example. We will see that a bit later for our project for eczema detection. You could see that like this line, here we have a line detector, which would really bring out the lines in that image, and then this would be used as one part of that feature vector. Especially for texture, there was one group from the University of Oxford that tries to really capture the texture characteristics. So in a paper by Zisserman and Varma, they use a texture descriptor, and they find out that the filter banks themselves do not provide enough information for the texture. They want to like boil it down a little bit clearer as a texture description, and then use that descriptor for supervised learning, or in their case for direct comparison of histograms. So they look, what they did is they look at those filter banks output, but then they applied the filters to their images and then did some clustering on the output. So their idea was that not in all kind of images or image regions there will be the same amount of filter bank results. So for example, in one kind of image you will never have a large response to one of the edge detector, and then it doesn't really need to be used at that case. So instead they clustered the output of those filter banks with just normal clustering algorithms like k-means, came up with 50 clusters, and this was kind of like their dictionary, that those features are characteristic in the images that they have looked to describe the textures. And then what they did is, for a new image, instead of using again the filter outputs, they used kind of a histogram of which cluster occurs in a neighborhood of some region. So this looks a bit like that. So you have a start input image. You will calculate your filter responses here. Then you will cluster your filter responses. So for example, if you're in the rotational invariant case, you will be in an 8-dimensional case here, and you will have to find clusters in the 8 dimension. If you use the full filter bank, you will have even a higher dimensional bank space. Then you have your cluster centers, and then you look at some larger region in the image, and you would calculate what are the nearest clusters centers in the neighborhood of that image. That will give you a histogram, and this histogram is actually your texture description. And in their paper first, they didn't use supervised learning, but they directly compared then the texture description to the textures that they had in different classes. So that would just be some histogram similarity measures. We will see that also then in the lecture, in the exercise. Okay, so this was the texture descriptor. Some other features, values that have been used since quite a long time. This gray level co-occurrence matrix, produced by Herlich, one of the first pioneers of image processing, and it just measures how often some specific combination of color values appear in a neighborhood. So you look at a larger neighborhood and you say, okay, I often have a white color next to a white color, and this is typical for the texture. Or I often have a white color next to a complete black color. That will be typical of the texture. And so for all combination of gray values, you will get some matrix of how often they occur next to each other, and that can be some characteristic of the texture behind. Usually you don't use the full matrix, but you can calculate some derived feature values from that matrix, for example, like contrast or homogeneity. And this is what is then commonly used as actual feature vector. Okay, another feature descriptor that's might be quite well known is so-called SIFT detector, the scale invariant feature transform. It actually consists of two tasks. So it's a detector of some specific points in the image, like I showed on the first slide there on the feature detection with the picture of the bird. So you select some specific points in your region, and you only calculate the detector at that point. The idea is that you then don't have too many feature values. Otherwise, if you use the feature detector at each pixel, you might get a very large feature vector. So you have those points, and those points then are converted to a descriptor, and for a descriptor you use the histogram of the gradient. We will just see in the next slide how this is calculated, and the result then is a 128-dimensional vector that captures the feature at that detector point. So for example, this can be used also for image stitching, or to find sub-images in a larger image, and it is scale invariant and rotation invariant. So here is an example. You have those this from the paper actually. So you have those photograph, and you have here some subregions, and the idea is now to find those subregions using those key descriptor. And so what happens is you detect your key points here, and you detect your descriptors, and then you try to match the descriptors with the key points, and you see those regions are then quite successfully found here in the image, for example, this point here. And you don't have to compare all the pixels, but you only have to compare the features, which makes it a bit more efficient, and also, of course, invariant for the rotation and the scaling. Internal, this SIFT feature descriptor uses a histogram of oriented gradients, also called HOG, and this is also by itself a feature detector that is often used and can, in our case, then also be used for texture description. It's also very often used for person detector. So one of the best person detector algorithms from, I would say, before neural network times, they were based on this histogram of oriented gradients together with support vector machines. So the idea is that you look at the gradient in the image. So the gradient will give you points where the intensity changes. So for example, also like edges. And then you calculate in which directions those gradient point, and you calculate the histogram of it. We will see the description in the next slide then, but here just what it looks like. So you also divide your image in some areas where you calculate those descriptors, and then you get a descriptor for each area here of the image. So calculation is actually done that you calculate the gradient, so you need the vector, so in x and y, so that would be the derivative actually in x and y gives you the component of the gradient. You divide the image into cells, and then you kind of compute the histogram of the gradient orientation. So it will tell you what direction is the gradient most prominently in this region of the image, or it could be more than one direction. You multiply the orientation by the gradient value so that you have larger responses for larger gradients, which means more meaningful features at that point. You normalize, and then you flatten everything into a feature vector, and this is just then your feature descriptor that you use for the comparison. Here's some examples. So here would be example test image. Here are the descriptor, and here we will later see how to use the descriptor by some supervised learning algorithms. So here supervised learning algorithm was a support vector machine, and it can point out which features are important for the positive and negative example. So positive example means if this feature is there, it's positive, it will be a person. And negative means if that feature is there, then it will probably not be a person. And you see, if the gradients are like that, and it looks kind of like a person. So if the gradients follow the outline of a person, then it probably is a person. And if the gradients, if you have something like here in the middle and you have a strong gradient here, then it cannot be normally a person, because you normally wouldn't have a line here in the middle. Also, I think this is an interesting paper that somebody came up with, is to try to find out what is actually the information in these Hock descriptors. And so they find a way to invert the descriptor. So if you have the Hock features, you can kind of reconstruct the image that would produce ideally those Hock features. And so this would be a reconstruction of the Hock features, and this would be the actual original image. And we can see that these features really capture quite well the basic information of that image here. And so this can also be used to find out when something goes wrong with your supervised learning algorithms. For example, they stumbled upon this test image, and suddenly their descriptor said, I see a car here. Quite unlikely that there is a car in this image of a duck here. So this would be the car, this would be the features. But now when you do the visualization backwards, what do these features describe? You get that image, and this image could very well look like a car. Okay, next we want to look at how we can use now these features on supervised classification. I would suggest we make a quick break here for 10 minutes, and maybe during the break, while you get your coffee, you could think about what methods you could use then for supervised classification, and maybe if they also then would work for semantic segmentation. Okay, so break for those 10 minutes, and maybe look at those two questions in the meantime. Okay, see you then. I think in this class it's often the case that some of you already have some machine learning experience and some machine learning lectures that you took, and some others might not. So what we will do is we try to outline the algorithms here that we use specifically for image processing, but you might have then get some deeper information on those algorithms when you have the machine learning lecture. Of course, we will look a bit more in detail than especially at the neural networks. On the convolutional neural networks, they're maybe more specific than for image processing. And yes, I got some ideas. Thank you for the feedback. So random forest classifier, base, those things would work. Support vector machines, we will look into that. This is one of the most commonly used or one of the most successful technique in image processing. Later, nowadays it's neural networks, but before that it was really support vector machine. Okay, so would they all work for semantic segmentation? Yes, probably most of the classifier algorithms would work for that. We will look at some and also some more simpler ones just to get an idea of what such a classifier actually looks like. So one of the very simplest classifier is nearest neighbor. The reason is it doesn't need much. You don't need to train much. You just need a distance function. What is the idea behind the nearest neighbors? You have some training examples from different classes. So here we have two classes, the blue square one and the red round one from class 1 and from class 2. And then you get a new example from your test set that you want to classify, and now you just calculate the distance to the nearest neighbor, and then you check what label does the nearest neighbor have. So for example here the nearest neighbor is blue, and so you will probably assign the test example as to belonging to the class 1. You can also use a k-nearest neighbor where you look at the not only at the direct neighbor or the nearest neighbor, but at the first k-nearest neighbors, for example 3. Then you would check what classes those 3 other examples are, and you take what the majority of them says. So you should always use that with an odd number of numbers here. Is it efficient? Not that efficient, because you need to calculate the distances to all examples from the training set, and that's going to be kind of quite a lot of computation power. One question was today, usually you use neural networks for everything. Unfortunately, that is quite often the case. So we will see some examples where we try up to come with some features ourselves, with some what we think more intelligent features, and with features that come up from neural networks. And unfortunately, almost is that the neural networks really perform better. So there is one saying also in reinforcement learning that with more data and learning more from data, you can usually with the time achieve more than if you try to put out some more maybe algorithm that has some more inside knowledge or domain knowledge, for example, to derive your feature. And so that at the end, usually the neural networks will get a better performance. One question was about interpretability, and this is really then a problem for neural networks, because it goes a bit now the research into that direction, that when the neural network says it's that and that class, you don't really know why, and you would try to interpret it better. And with some of the other algorithms, you might have a better idea of why the algorithms come to that result. Okay, but let's look at some other classifier algorithms. One is just a linear classifier. What is a linear classifier? So this will be just some line here, some straight line going in the dimensional space. So it actually would be a hyperplane in the dimensional space of your features that will divide those two classes. And you can calculate such a straight line or hyperplane by this formula here. So w times x plus b, and then this will give you this hyperplane, and this function is the sine function that will tell you if you put in some x, it will be on that side of the hyperplane or on the other side of the hyperplane. So for example, if the sign is positive, you will be on the blue side. If it's negative, it's on the red side. And if you have then some new example that you want to classify, you just have to calculate this and you see on which side that you are. There was a question, linear classifier equals to regression. No, that is not the case. So a classifier would here just give you the classes back. So just two answers here, -1, +1, which says it's that class or it's not that class, and a regression, then it would be more that you have as a result some specific value. So logistic regression would be similar, yes, like a linear classifier. So sorry, usually regression is more used that you want to derive some specific value, another class, but in the binary case that would be a logistic regression. And generally a classifier will give you one of n classes if you have more classes, and it will be binary if you just have two classes here. Okay, now from this straight hyperplane that we have to separate our classes, the question is, what is the best one? Because there might be a lot of choices and they might all work on the training set, but you want a choice that will also work best in the future when you see unseen samples that are not included in the training set. And one algorithm that does this is the support vector machine. So for all the possible choices of linear functions that separate your values, you choose that one that has the largest distance then between the classes. So what does this mean? So in this example, we have two-dimensional features. We have classes here and we have the other class here. Fortunately, they're linearly separable so that we can put a straight line between them that will separate them, and we see that we have different possibilities to put this line here. So which one should we take? And for the support vector machine, we take the one that separates them best. So what does this mean? So if you put the line anywhere here, then we can calculate the distances of the nearest points on both sides to the actual plane here. And so for example, if you would put the line here, then it will be nearer to both of those points. And then it will be less good because then the distances between the classes is not as large. So this is what the support vector machine does. It calculates for every possible line here a margin, which is the separation in this direction orthogonal to the hyperplane here of the vectors from one class and from the other class. And those vectors that actually determine where this line will be put are called the support vectors. So you can see that the other vectors here, once you have the support vector, you actually don't need the other samples here because they will not influence the line here. It will be only influenced by the nearest points here, the support vectors. And so it will be an optimization so that the value of the margin is largest. We will not look here how you do such a optimization and the math involved here, but just from the idea is that the support vector machine will generate the hyperplane that gives the largest margins of all possible hyperplanes. Sometimes it's not really possible that the two classes are linear separable. Then you have two possibilities. One is to use so-called soft margin support vector machine, and the other possibility is then to use some kernel trick where you put the samples into a higher dimensional space. So for the soft margin support vector machine, you just have two criteria that you want to optimize. You still want to optimize a large margin between the support vectors, but you also accept that some of the samples can be on the wrong side. And for those samples that are on the wrong side, you get a penalty, and you try to optimize that you have as much as possible no values on the opposite side, so as little penalty as possible. And so you will optimize then for both of those criteria of large margin and minimal penalty. This is called the soft margin support vector machine. The other possibility is that you use some function, some base function actually, that will transform your samples into a higher dimensional space. So what can you do when your training samples are like that? So you have all the blue classes outside this circle here, and you have all the red class samples inside, and obviously there is no hyperplane to do that, to separate them. So what you can do is you can go from this two-dimensional space to this three-dimensional space, and then find some hyperplane in the three-dimensional space that will actually divide those two classes here. And this can be done automatically with some special basic functions, or you could also come up with, if you have a specific problem, with a function that works here. Like here, for example, the third dimension could be just the distance from the center, and if you have the distance from the center, then you will see that you will easily have a hyperplane that separates them, because all of those have a higher distance. Okay, these are your two possibilities. If you have a problem where the classes are not linearly separable, and you probably will have that in most of the problems, because the data will not be that good, so that you have to come up of using those approaches. Okay, so these were some examples for classifier algorithms. Next week we will look at the neural network as the next one for the same problem. So now if you want to do this for semantic segmentation, then one problem is a bit that we will have to do that at each point in our image, and usually the calculation of the feature will not come from the whole image, but just from some sample around the neighborhood of that image. So what we need then is a kind of sliding window approach. So we have a window that goes through all the subregions of the image, and we calculate the features for each pixel from the local neighborhood. That will give you the features for the center of the pixel, and then we can classify that as center pixels. So sliding window idea is kind of like that we look at just a sample of the image that we classify. And of course, that can be quite exhaustive in the computation, that you have to do that for each pixel. So sometimes you can also use it that you just divide the image cursor into some blocks, and then just classify the blocks instead of each pixel individually. Okay, as a last point today, I will like to give some example of our own research where we would try to detect eczema. So today we look at the results of support vector machines for this task, and next week we will look at the neural networks for the same task. So most of the experiments on the support vector machine here were done by a student for his master's thesis, and we will look at some of those results here. So what is the idea? The idea is we have a patient. He has eczema, so this is some condition on the skin, and we would like to detect that. Why do we like to detect that? For example, what happens is that some doctors use some score of how extreme or how bad the illness is. And this score, for example, uses how much of the hand area is eczema and how much is not. And this is something that is not that easily calculatable for a doctor by just looking at the hand, so a computer might be able to help him here. And also we can then calculate this score for objectively, and that might also help the doctor. Because if the illness is very severe, then maybe the insurance will pay more than if it's not, and then it's a good idea to have some object method that can detect the severeness of the of the illness. So that was the idea here. Okay, so it's supervised learning, so we need data. So if we need data for supervised learning for semantic segmentation, we need the data for every pixel. So this can be a little bit of a problem because it's a lot of work to actually mark the eczema here. So the data that we used is twofold. So on one side we have really the marked eczema here, and on the other hand we also need to separate the hands from the background, which we can do a bit semi-automatically, but we also use that as a as input image. So at the end we want to classify 3 classes in the image. Is it a background, is it hand without eczema, or is it eczema? So we need the data. So in order to get the data, we wrote some web application so that doctors can use to mark some eczema in images. And so this was distributed to some doctors and also to some medical students that they go through the data set, and all of them mark it there. Well, it seems that we were not entirely good with the description of what was expected, so some of the results were like that, and this is not so easily usable then for the semantic segmentation. So in the second round we tried to be a bit more specific, but still then we had a bit of a problem that like here this is the same patient, and this has 4 different doctors, and they make a different segmentation here. So then what we did then is to combine the data from different doctors and have some voting, like if 50% said it was eczema, then we used it as a label for eczema. Also what we did is we made a new method of having more standardized images. Our very high technology photo box here, so that people can just put the hand in and it will automatically make an image from the hands and store it then in a database. And this was installed then at the University Hospital of Zurich, and this helped us a bit to get images with the same quality, so we also have the same resolution. We had a higher resolution. We selected a greener background because it's easier to segment that. Okay, now on those images we tried to do the classification, and when we first approached the project we really looked at the texture classification and saw what can we do. Like the eczema looks like some kind of texture, it's very local, so we would like to see if we can do that with texture classification. And this was just the approach that I presented a bit earlier with those text on features from the filter responses, text on clustering, and then the histogram of that on textons. And then, because in the meantime since they wrote that article, support vector machine proved to be much better, or a bit of standard in image processing, so we try to do the same then with the support vector machines. So that just means that once we have calculated the features, instead of comparing histogram of texture distribution like in the original paper, we then use support vector machine to find a classifier to classify the features that we trained. It was trained. So we used a different experiment. So one was just like a baseline, same features than Varma and Zisserman used, but then just using the support vector machine instead of the histogram comparison. Then we used those gray level occurrences matrix and also some more statistics like color moments that would be just the mean color, and also derivations first and second moment of those color distributions. And then we try to use different combinations of those features, including then at the end all features, and also some more data cleaning in the beginning to see what happens. And we experiment with different support vector machines, so it's the linear support vector machines with soft margin, or those with polynomial kernel, which will go to the higher dimensional space here. So actually we will look at metrics a bit more in the next lecture, but here just a quick summary what you want to look at if you do such an experiment. You have different kind of results. You have true positives. That would mean that you labeled it as positive eczema, and it is actually also detected as a eczema, and so there would be a true positive, or doesn't have a label and also doesn't detect a label. That would be true negative, so that would be your correct examples, which are summarized in the accuracy. And then you have two kind of mistakes. So false negative would be you say it's not eczema, but it actually is eczema, or on the other hand you say it's eczema, but it's not. So that would be a false positive. And from those you can also look at different metrics. As I said, we will look at that in the next lecture a bit more, and then you usually use some score that you want to optimize for your classification. It's often not accuracy, because in cases that you have not so much eczema, and then you will have a lot of true negatives, then the accuracy will often be very high, but it will not mean that much. So you have to be careful if you have so-called skewed data, that you have more from one class than from another class. So first we look at textons only. I think it doesn't look bad when you look at the results here. So some large areas are correct, but also a lot of false positive here, which bring the score a bit down. Then we try to use some more features, those color moments and those co-occurrences matrices, and so with using that, scores went up actually in all directions. So this was already then better as the original texton scores. If we use everything together, then some scores are better, some not, so it was not really a definitive better to use the original textons than from the paper. And if you put everything together, then we actually did get the best result, so then that the classifier was kind of able to choose from the feature which features were most important then to do the correct classification here. But of course, larger features also mean larger processing time, and in this case, training the support vector machine was a couple of days until you could get a result. Yeah. So here's some examples from the scores here. What from the scores is best and worst. So actually, we always get the best scores when there is a lot of eczema. So we will also detect a lot of eczema, and there are some mistakes, but compared then to the area that was correct, this will still get a very high value on those scores. The worst scores are achieved when there is almost no eczema. Like here is some eczema, and the algorithm then detects it somewhere else, then it's just completely wrong, and it will be a score of like 0 mostly in all of them. Okay, this will be all for the theory part of the lecture today. So the exercise today will be to look at this texture segmentation using features, and then supervised learning with different types of feature vectors to use, and we will use that on the describable texture data set. We will also continue with that next week on neural network, and additionally there will be a bit larger homework then for the second part of the lecture, which will be this texture segmentation with convolutional neural networks, similar to the homework that you had in the first part of the lecture. Okay, that's all for the theory. Maybe another quick break of 5 minutes this time, and then I will come back and we can quickly discuss and look at the exercise from last week. Let me just quickly reset the timer here. So it's okay, then back in 5 minutes with the exercise.